Okay, so you should see my screen. Can someone confirm?
Yes, sir, we can see.
Wonderful. Okay, so what I've done is, since there were a lot of questions yesterday about what is the associativity, essentially, I've added a few slides on what associativity function application should have and such. So these are in there. So if you git pull, right, you have to do a git pull so that you get the latest slides. And then if you go through it, you will see that there are additional material. So hopefully this is useful when you refresh the material later for the final exam. Okay, so as I mentioned before, you can always look at a type signature, a function type is signature that looks like this, and you can have two readings of this. You can sort of look at it as, oh, this is a function that takes 1, 2, 3 integer arguments and then returns an integer argument, right? But you can also read it differently, which is that because the function types are right associative, so you will read it like this, where you read it as a function that takes a single integer and returns a function that takes two arguments and then returns an integer, right? So you can essentially read the same type as two different ways. Okay, so oftentimes what happens is in most of the cases we will sort of stick to just talking about function taking two arguments, but it is also useful at some point to read it the other way, because it opens up a whole box of possibilities that aren't typically expressible with in any other languages, right? Where you sort of say, I have a function, it takes two arguments, I have to give it two arguments. Here you can just partially apply the function, and then you get a separate function which is now specialized, right? One of the arguments is applied and specialized. So the example that we were looking at is this artificial example where this takes three arguments and then returns the sum of these arguments. You can specialize this function by just applying the first argument, in which case it returns a function that takes two arguments, returns the sum of those arguments plus one, right? So just to see how this works, foo now takes two arguments, right? Because you've applied the x argument, so it's a function that takes two arguments, and then returns the sum of the two arguments plus one. So sum of the two arguments is 5 plus 1 is 6, right? So here it works as you would expect. So these are artificial examples, but you can sort of think about more still artificial but more useful sort of examples. So recall that we had defined add as a function that takes two arguments and returns a sum. Now you can define successor and predecessor as just a partially applied add function. So just to recall, add is defined here, right? So it is, I've written it in a weird way, but you can just write it as let add xy equals x plus y, right? And what I'm doing here is I'm using that add function and partially applying it with just one. So you will get a function in return which takes one argument and returns the that particular argument plus one, right? And predecessor similarly takes that argument, subtracts, returns the value which is one minus the argument that you supplied. So you can sort of see this is useful, right? This is a useful building block for constructing specialized functions from very general functions. And you can obviously see that suc of 10 is 11 and pred is predecessor of 10 is 9, right? This works just naturally. Okay, so that is partial application. Again, we have not seen real uses of partial application. We will sort of see more bigger uses as we look at more examples in the rest of the lectures. But now I want to focus on okay. So I want to focus on doing something which we do often in mathematical functions, right? We write recursive functions in mathematics often. And it would be nice to write recursive functions in the programming language as well. And OCaml does allow recursive functions. And the only difference in syntax is if you want to declare a recursive function, you have to use this rec keyword. So letrec defines a recursive function. And what is a recursive function? Recursive function is a function that can call itself. Okay. And you'll see that this is a very powerful concept. So here is a simple use of a recursive function. So what I'm doing here is I'm computing the sum of first n numbers, right? So observe first thing, this is a recursive function. So I write letrec, right? Sum of first n is the function name. It takes one argument n. And how do you compute the sum of first n numbers? You have a base case and one recursive case, right? The base case is when does the loop actually terminate? So you're doing recursion. So it's going to call itself. When does the recursion terminate? If n is 0, I'm also considering less than 0. But typically, if n is 0, then you return 0. Sum of first 0 numbers is 0, right? Otherwise, you take that n, add it with the recursive invocation of the same function, right? Sum of first n, it's recursively calling itself with n minus 1. Right. So what this is going to do is first, if you say, okay, so let's go step by step. So what's the type of this function? So the type of this function is int or int. Why? It takes an integer, right, and then returns an integer. You can just look at that. Again, if you go back to the static semantics of if rule, this should also be an integer because since the true branch is an integer, the false should also be an integer. Okay. So we have defined a function. So this function takes an integer, returns an integer. So what happens when you do sum of first and 5? The first sum of first 5 numbers is 15. So you get 15. But it would be nice to see how this actually expands to, right? We can see how it expands to. So you sort of have in it first for the first call, n would be 5. So this condition would not be true. N is not less than 0. So you go to else branch. So 5 plus sum of first and 4, right? You recursively apply it. This won't match. So you go to the else branch. So you will have 4 plus. So this keeps expanding, right? 5 plus 4 plus 3 plus 2 plus 1. And finally you'll have 0. And that's how this expands to. So you can expand it by hand. So there is a question, sir, what if we don't use rec, write the same thing, what would be its run? So what will happen is, so when you do this, right, actually this, I think this will not complain. So the reason is that the kernel has a definition in the environment. So forget what I said, but let's start clearing the output, right? And I just want to do this. So the question is, what if I don't have the rec keyword? So what is the rec keyword actually telling OCaml, right? When you don't have the rec keyword, it is going to look for a definition of sum of first n in its scope, right? Which is not this function. So it says, okay, I will look for some other definition elsewhere. Obviously, there is not going to be a sum of first n except this definition. So if you try to compile this, so yeah, so actually OCaml is very helpful now. Its error messages are much more saner than when I used to start programming in OCaml. What it says is this particular invocation, right? This particular reference to sum of first n is unbound. So I can't find where that particular variable is. I don't know what that thing is. And OCaml helpfully gives you a hint, right? If this is a recursive function, then you should add rec keyword on line 1. So line 1, it is sort of pointing to here. I think that should clear your doubts. So if you add the rec keyword, then the function you are defining comes in the scope of the body of the function. So you can refer to the actual function that you're defining in the body. So that's the only difference between rec keyword and not having the rec keyword. Okay. So just to continue, so sum of first 10, 5 is 15. And OCaml top level, which is what we are sort of wrapping around in this Jupyter notebook, provides support for tracing functions. So you can actually see what are the calls being invoked to the function and what are the return values. So there is this meta command. So in Jupyter, there are a few meta commands where the meta commands start with trace. So this is not OCaml, right? This is not OCaml syntax. This is just the syntax to interact with the top level. So we are typing code and it's sort of sending it to the OCaml compiler and getting back, right? This intermediate thing is called the top level. And you can sort of communicate with the top level using some meta commands, right? So hash trace is one. And what you're saying with this hash trace is please trace the execution of sum of first and function. Okay, so um, ignore this double semicolon for the moment. I will come back to what a double semicolon means. It's just a matter of saying this is one command and do the second command, but it can be a little bit confusing when to use double semicolon and such. Let's ignore it, right? You can always write it as two separate boxes. In two separate boxes, it will work.
Sir?
Yeah.
Sir, my internet was a little flawed a few minutes
Yeah.
back. Can you
Okay.
explain the rec keyword explanation again?
Yeah, sure. So if you don't use rec, what will happen? I have to do this again, but that's fine. If you don't use rec, okay. So I'm going to remove rec. Okay. So what OCaml is trying to do is try to look for a definition of sum of first n in scope, right? Because I don't use rec, this particular function itself is not defined. So if you try to compile it, OCaml is going to complain saying, I can't find a value of this particular name, right? So that is not in scope. And OCaml gives you a hint, right? If you're using a recursive definition, you should add a rec keyword. So the only difference between recursive and non-recursive functions is when you define a recursive function, the name that you're defining, right? The name that you're defining is available in the body of the function definition. Like now, because I use rec, this name, sum of first n, is available to be used in the body. So I can call the function itself. So this works. Is that clear?
Sir?
Yeah.
Sir? Sir, am I
Yeah,
audible?
you are.
Sir, so like, but when we have variables, when we check in the scope, and if we don't get it, we go to a higher scope, right? Why
Yeah,
are we doing that in this case?
no, we are doing that, but there are no definitions in the scope. So the scope is this, right? When I remove this, right? Let's assume this
Yes,
rec
sir.
keyword is not there. This particular function is not yet defined, right? In when I come to type checking this part, when the compiler looks at the body, right? So this particular thing is not yet defined because we are still defining the body, right? So it's like a self-referential thing, right? So you are building a building and you are saying, oh, this building, I'm going to talk about the same thing that I'm constructing. So in OCaml, you can only, by default, you can only talk about things that have been constructed, right? So if you don't use the rec keyword, this definition does not come in scope, right? This is not yet defined. So OCaml is going to look for stuff that is defined above here and anything else previously. So there is not going to be any function called sum
Okay.
of first n, right? So, okay, good question. So was there another question?
Okay, thank you, sir.
Sir,
Yeah, Anirudh had a question. What if you want to use two functions which refer to each other? We can do that. I will show an example later. Okay, so Raghu had a question, is it?
so like in this case, if before this I declare another function of the same
Hmm.
sum of
Hmm.
first n,
Yeah.
it'll work or it'll give some multiple declaration errors.
It won't, right? Because we have this concept of shadowing. Really good question. So these are exam questions, right? So I might even directly ask those in the final exam. So let's try it out. So let's open a new thing. Let me make it a little bit bigger. So I want to define, let's say I have some bar, right, which is going to return 5. And I actually want to write a recursive function for which I, um, okay, so here is a definition, which sort of captures what you want to do. Is that right? Right. So we don't have a rec. If I had a rec, then this particular call will refer to the same function, right? But now if I don't have rec, this bar is going to refer to this bar. And if you execute it, let's actually execute bar, you'll get 5. Okay. So what is happening here is when I apply bar on unit value, this is going to be referred to this bar, whose body bar refers to this bar, right? It's simply, there is no multiple definition. There is nothing, because you can just name the same thing again. So the question is, what will happen if I do this? Any guesses? You've seen recursive functions now. So I changed this to a recursive function. So this bar is no longer going to refer to this bar because I am defining a recursive, infinite loop. Abhishek has okay, very nice. So a lot of good answers. So infinite loop, right? Because I'm no longer referring to this. So this is not even needed, right? So this is going to be, actually ignore this thing for now, but it's infinite loop. I'll come back to what that thing is. But this is going to run infinitely and not terminate. I don't want to do that now because I want to, then I will have to kill the, actually I'll do that just to show you how to recover from this, right? You will often write a function which is going to recurse infinitely. So here, the thing is, it is going into an infinite loop and it's not going to, I don't know whether you've done very serious C programming where you had stack overflows, right? Um, this thing does not stack overflow. It's just spinning, and my fan is sort of starting to spin up. It's actually trying to use a lot of memory, CPU. So if this comes up and you are sort of confused what is happening, look at this circles here, right? It's filled here. It's sort of telling you the status of the kernel. So we are sort of going into this we are sort of digressing from what we should be doing, but I think this is important. So the way Jupyter Notebook actually works is there is a OCaml interpreter that is sitting in the background. Okay, and Jupyter calls those kernels, and we have a kernel. We have OCaml 410 interpreters that is sitting in the back that is executing our program. And what you see here is that it says kernel is busy, right? It is not returning. It is doing this infinite loop. So in order to recover, you just stop executing the kernel, right? And what has happened is you get an error message which says that it's been interrupted. So if you get into a situation where you're writing infinite loops, try to look at the status of this kernel. I mean, kernel is idle now, right? If it is busy and it's not returning, you have an infinite loop somewhere, and you terminate the program by stopping the kernel, and you'll get an error message here, and then you can continue. Okay, so I will move on. I think I should not be here. Okay, so let's go back to what we were doing. So we are doing this recursive function. Okay. Okay, so recursive function, this should work, right? And now you can trace the function. What is going to happen here? So if you look at this one, because I've enabled tracing, you can see that Jupyter first says this function is being traced, and you can see the input and the output. So you call the function with 3 first, and the recursive call 2, recursive call 1, recursive call 0, and the recursive call to 0 returns with 0. Then the first one returns with 1 because it's 0 plus 1. And the second one returns with 3 because it is 0 plus 1 plus 2, which is 3. And the last call returns, actually the first call returns with 6 because it is 0 plus 1 plus 2 plus 3. Okay, so you can actually see the input and output flow. Personally speaking, I haven't used this feature extensively. It is often easier to just work it out on paper what is happening, right? But if you are not able to make progress and you just want to see what the function is doing, this is probably helpful. Okay, so tracing function is probably helpful. And you can, now that it is being traced, we can ask Jupyter to no longer trace it. So you can say untrace this function and it will stop producing these log messages. Okay, so yeah, I call it exercise, but the answer is here. So the one recurrence relation that we all know is Fibonacci, right? So what is the recurrence relation for that? Any Fibonacci number is fib of n minus 1 plus fib of n minus 2. That is how you compute the nth Fibonacci number, right? And we have base cases. So if n is 0, then 0. And if n is 1, then 1. So it produces, I mean, this is a recursive function to compute the Fibonacci, right? So, and we write it in very natural fashion. So if you write a mathematical equation, you would write it as a recurrence relation and the base cases, right? So, and we write the exact same thing here, except that we have to do some sort of syntactic differences to say that this is a recursive function. It takes an n. If n is 0, then 0. And one other thing that I want to say is, let's look at this one, right? If n is 0, then 0, that is fine. I am using else if here, right? But I haven't told you that OCaml has else if. So the way to actually read this is there is no else if in OCaml. It is just a matter of scope. It is just a matter of how you parse it. So we only have if and else. So if n is 0, then 0, else this expression, this whole expression, right? Which is again going to check if n is 1, then 1, else the bracket comes here. Okay, so else fib of n minus 2 plus fib of n minus 1. So we don't have else if in OCaml, but you can sort of write it as if else if exists. Okay, so that's the so that is the thing with else if. So okay, so else if is here, and we know fib of 10 is 55. Okay, so 55. So here is another concept in OCaml. So you can write assertions in OCaml where assertions are going to be a function. Okay, so they are a function that take a Boolean value and then return unit value if it is true. If it is false, they are going to throw an error. Okay, so that's what is going to happen. So we know that fib of 10 is 55. So this equality will be true. So nothing will happen here. So if I write it, it will just return the unit value, right? So assert is a function that takes some Boolean and returns a unit value. If the input is true, then it returns a unit value. It is like nothing. If it is false, it is going to throw an exception, right? We will cover exceptions later, but you can sort of think about this as a failure case, right? It's going to throw an exception saying, oh, there is some error here. Yeah, so assert failure at line 16. Sorry, box 16. The box is 16. There is only one line and the first character, the 0th character. So that's what this is saying. So you can use assertions to check whether your implementation is correct, right? So you write some function, you want to test it on very simple inputs. you can use assertion. Right? So assertion is a nice handy way to quickly check whether something works. Um, okay, so I think that is assertion. Let's move on. Anirudh had a question earlier about what if we want to use two functions that refer to each other. So we have a facility in OCaml for that. It is known as mutually recursive functions. So mutually recursive is you can have a set of functions actually. It doesn't need to be two. It can be n functions that need to call each other. Okay. Um, in practice, this doesn't come that often. Okay, so that's I'll also put that out there. So what are we doing here? We are defining. So this is a very odd way to define even and odd. Okay, so it's a linear time function to compute whether something is even or odd. This is not efficient, right? This is just there to show you how mutually recursive functions work. So what are we doing? So let's just look at the definition of even for now. So even is a recursive function, right? That takes an integer n. If n is 0, then we know 0 is even, right? So true. So that's the base case. And now let's look at odd, right? Let's ignore this and for now. Let's look at odd. If you give me an n, and if n is 0, then we know that 0 is an even number. So you return false. So these are the two base cases for the two functions, right? What are the recursive cases? If let's go back to even. If n is not 0, then we just ask whether n minus 1 is odd, right? If n is even, then n minus 1 has to be odd, then n minus 2 has to be even, then n minus 3 has to be odd, and so on, right? We are simply using that particular idea. So for any other n which is not 0, we call odd of n minus 1, which calls this function. And similarly, for any n that is not a 0, if you want to check whether that number is odd, we call even of n minus 1. And what happens is, if you give a large number, this mutually calls each other, right? And the way you allow this mutual recursion is you start the first function definition with the letrec, right? And any other mutually recursive function, you start with and. So letrec even function, you define the body of the function, and for the subsequent function, you just define it as and odd, and you can define something more, right? The syntax is the first function has to be letrec, then the rest of the subsequent functions in the mutually recursive set of functions will have to use and. So you get two functions because we are defining two functions. You can call either of them, right? Both of them, and the call will automatically, based on the input, call each other. Yeah, so I don't have an example, but you can sort of play around with it, right? You can give it some number and then see how the tracing works. So trace both functions, right? And then call it with some number. You will see that the calls will alternate between even and odd. I'll leave that as an exercise for you to play with. Okay, so that's that. Now, so far we've been sort of talking about things in the abstract all the time, right? We are saying, oh, these are functions, everything is functional, everything is so nice, you can take any mathematical function and translate it. But sometimes we also need to execute our functions, right? So we do want to run our functions and get the output. So we do that by compiling our program to actual machines that we have, right? So we also have to think about practical concerns at that point. And in particular, so we introduced this concept of recursion, and we said, oh, you can use recursion to write these nice programs. But practically what happens is you have to be a little bit careful about recursion because you have this concept of recursing too deep. Okay, so let's look at what that too deep is. Let's just invoke first of sum of first 10 with a very large number. I think this is a million. Yeah, it's a million. Um, yeah, one thing that OCaml allows is it's very hard to read the number, so you can use underscore in between. This is quite an oddity, but it makes reading the numbers easier. This is also an integer constant, right? And it's just a million. So I'm going to invoke this function which computes the first sum of first million numbers. So let's see what happens. So we get an error immediately, right? And the error says that stack overflow during evaluation. Do you have a looping recursion? Is what the compiler says. And raised by primitive operation at file 9. So this 9 is actually referring to the ninth cell where sum of first 10 is defined. So just to give you an idea of where the error is being complained, if you look at, yeah, 9 is where we define sum of first 10. So that's why it is complaining at 9. And what is happening here is you can see that from cell 9, we have a very deep call stack, right? I assume that you have studied call stacks and other things when you studied C, right? Just like how C functions work, when you call foo and calls bar, you have a frame for foo on the stack, and you have another frame for bar on the stack, right? So these two are stack frames, and stack is a system resource, right? So you have a limited resource for stack, and as you will study in operating systems in this semester, what happens is there's only a limited amount of memory. So your stack keeps growing and growing and growing, and at some point it is going to hit the limit for your stack overflow. So it's going to hit that limit and say, okay, I can't recurse anymore. So I have to give up. And this is OCaml's way of giving up, right? It says stack overflow during evaluation, and it produces a very deep stack. And you can sort of see where the calls are coming from. So let's dig in a little bit into this, right? Where is the stack buildup actually happening? So if you look at the definition of sum of first n, which takes n as an argument, so base case is simple, right? And the recursive case, if you sort of stare at just the lines here, right? Every time you're going to call this recursive function, this function will be called, it has to return, and then you're going to perform that particular result plus n, right? So abstractly, there is some work left to do when the recursive call returns. So you call this function, it is going to compute and then come back with a value, an integer, and you're going to take this n and add it to that result. So this particular work that is left to do after the recursive call returns is the source of the problem, right? It is sort of the work that you have to do after the call returns. So this ends up being built up as stack. So here is a pictorial representation of what is happening, right? So when you call sum of first and 5, you're going to leave the work that you have to add 5 to the recursive call here, and you're going to call sum of first and 4, and which is going to leave the work that you have to add 4 to the result and call 3, and it is going to leave plus 3 here, call 2 plus 2 here, call 1 plus 1 here. 0 is going to automatically return, right? So because it's the base case, so there is no work here. And then this returns with 0, and you're going to add it with 1. 0 plus 1 is 1, which is going to return here, and you're going to add it with 2. 1 plus 2 is 3, it returns 3 here. 3 plus 3 is 6. 6 plus 4 is 10. 10 plus 5 is 15. So this work that we are building up is the source of the problem. Okay, so that's the reason why our stack actually overflows. And the question that you want to ask yourself is, okay, so this is not great, right? So I want to write recursive programs. Maybe you want to write something else as well. But is it the case that whenever I write a recursive program, I have to be really careful about building up work? Yes, you have to be careful about writing recursive programs that take a very large input. It may stack overflow, but does that mean there is no way to write efficient recursive programs? No, there is indeed a way, and this is a standard concept in a lot of functional languages, but also this is true with um, languages like JavaScript and all these other languages where you have recursion, right? Actually, it is also true with C. So there is this concept of tail recursion, right? So abstractly, tail recursion is this concept where we avoid this little bit of work that is left to do when we make a recursive call. As I mentioned, the problem here is this work that we leave here, right? So this +4, +3, +2, +1. If we can avoid that work, leaving that little piece of work that has to be done after we come back, then we won't have to, we can do some sort of optimizations later, right? So the question is, how do we rewrite our programs such that we don't leave this little bit of work? And in the case of the sum of first and tail rec, here is how you have to rewrite your program, right? The idea is to use a accumulator. An accumulator is sort of an auxiliary variable that sort of keeps track of some other information along with your recursion. Okay, so let's go through the function step by step so that we understand what's happening. So this is also a recursive function, right? And I define this function as sum of first and tail rec. It's a new function. It is not a function that we are defining there. It is semantically the same. It is going to compute the sum of first n, but I just name it differently. Along with the n parameter, it takes an accumulator as a parameter. Okay, so what is this accumulator? This accumulator is going to hold the intermediate results. Okay, it is going to hold the sum of it is actually going to hold the value that is the sum up to the current recursion level. Okay, so let's call it at that, and we'll see how that works, right? So if n is 0, then you just simply return the accumulator, right? You built up the sum in this auxiliary value, so you simply return that accumulator. So that's the base case, and the recursive case is interesting, right? Here is where the ingenuity is. So you recursively call sum of first and tail rec, right? And you call with n minus 1, that is the same as the earlier one. And here is what we are doing differently, right? Instead of saying n plus the recursive call, we are actually saying call the sum of first and tail rec with n plus accumulator as an argument, right? You will get whatever accumulator that you have at that point. You take the current n and sum it up with that accumulator, and you pass that as the argument to the recursive call, right? So the main difference, what is happening here is this addition is being done before the recursive call, right? The addition is done. So there is no work that is left to do after the recursive call returns. You just return the value, right? So you've called it, it returns a value, you just simply return it over to your caller. And that is what makes all the difference, right? So this n plus accumulator sort of keeps accumulating the result. I mean, if I were to ask you to write this program in, say, C, right, you will declare what? Int sum equals 0, and then you'll keep incrementing the value in the sum variable, right? And you'll keep on incrementing, and once the loop is done, you just return the value of the sum variable. This is precisely that idea written in the functional style, where you pass the value of this sum variable, the accumulator variable, over to the recursive call, and you finally return the accumulator as the result. And this accumulator just bubbles up all the way to the top level. So, okay, so we have this additional argument accumulator, right? So, what is the initial value of the accumulator? So when you write the for loop for computing sum of n variables, you will say sum equals 0. And similarly, when we call, the first function the first time, we set accumulator to 0 here. So is it like saving time by saving memory in recursive stack? No, it's not. It's not saving time. It's actually going to save memory. So let me tell you what it does. Um, Good question. So let me finish what I was saying, and then I'll get back to your question, Rudra, Rudra Pritesh. Um, so here, this is a standard trick that we use. This is a two-argument function, right? Sum of tail rect takes a first argument and second argument. This is sort of the internal accumulator argument, right? So we don't want to expose it to the user. We want to sort of hide that in the interface, and we know what the initial value is going to be. So we pass 0, but we use the same function name here, right? So we can use the same function name. This particular function is not a recursive function. I'm just defining a new function with the same name that just takes a single argument n and calls this function with 0 and n. Of course, I could have named it as foo or something, right? So it's just the same. I'm just shadowing the previous definition. So there is a lot going on here. I want you to have a close look at this function, right? And then let me finish this. You can take your time and ask questions, but I will sort of finish what I'm doing now. So this is the value for which we failed earlier. Actually, this is 1 billion. We do 1 million for a start. So I'm calling this tail recursive function. So what happens? It returns immediately, right? So um, Ravi Gupta. So yeah, so OCaml has fixed size integers, yes, and we are running on a 64-bit machine. OCaml's integer is 63 bits long for a weird reason, but yes, it has machine-sized integers. So the integer sizes are 31 bits and 63 bits. Yeah, so we do have fixed size integers. So this returns immediately, right? And there is polymorphism in OCaml. We will come back to that in the next lecture. Yes. So there is no polymorphism going on here, just for others. So this particular function, I just want you to recognize that this particular function that I've written is as efficient as the C function that you can do, right? So the OCaml compiler is going to optimize it. So the question is, why aren't we building stack, right? So there was a question that was asked earlier, which is like, so is it like saving time by saving memory in the recursive stack? We are not actually saving time. We are actually saving memory. So what is happening here is, what we do here is tail recursion, right? There is no work that is necessary after we do the tail call, sorry, the recursive call. So the such a recursive call is known as a tail call. So why do we call it tail? It is the last thing that we are doing, right? In this function, in this branch, the recursive call is the last thing that we are doing, right? So there is no work left to do when the recursive call returns, except return the result back to the caller, right? So this is just one part of the optimization. What the compiler actually does, this is the important bit, right? Whenever the compiler can see that the recursive call is the last thing that it's doing, before actually making the recursive call, it pops the current frame and then does the call. So I don't know whether I have, okay. So instead of building up stack like this, right? Instead of building up stack like this, it is going to create a stack frame for sum of first and tailrec 5. But then it observes that the call is at the tail position, right? So it's simply going to pop this frame and make the call for 4, and simply pop the frame, make the call for 3, pop the frame, make the call for 2, and so on. So it is not actually building up stack, right? So it is in fact saving memory. So you can run this thing for any big number and it will just work. So the point to take away here is this particular function is as efficient as writing a for loop in C, right? So OCaml compiler does all the work. This is running for a while because this is just a big number. We are just computing for a while. So tail recursive functions are as efficient as for loops in C, right? So that is one of the things that you sort of have to learn to do in OCaml, we tend to write recursive functions all the time, right? So for loops are very rarely used. We do have for loops in OCaml, but we rarely write for loops. I think that's not a thing that we actually use often. So recursion is the way to go, right? When you write these things, we always prefer recursive implementations because they are much more natural. So in mathematics, you study recursive functions, right? Mathematical notation doesn't say use for loops and while loops and do while loops and whatnot. So we like to have the same sort of reasoning there, but the OCaml compiler in conjunction with you doing some work, right? It's not magically transforming a, non-tail recursive function into a tail recursive function. You have to do the work, but if you can do a little bit of work, the compiler will do the rest for you. Okay, so I think that is what I had for this lecture. Any questions on this? I think this is a little bit. It may take you a little bit of time to catch it, or you might just get it on the first go. But this is sort of the natural way of programming recursive functions in OCaml. Is popping a stack frame in case of a tail call specific to the OK? Good question. So this is so this tail call optimization is a general compiler optimization. So I don't know whether you will study tail call optimizations in the compiler course. GCC also does tail call optimizations. So, but you have to enable it explicitly, and Clang does it as well. So these are a standard set of optimization that any compiler can do. If you know that when you perform the recursive call, there is no work left to do, right? At that point, you can pop it. So GCC does do it. And more importantly, JavaScript is a very much a functional language compared to C or Java. And these JavaScript engines now have proper tail call optimizations. I mean, this is very recently added. So you can write tail recursive exploration of some linked list style programs and it just work. Earlier, it used to Stack Overflow very easily. Is in some of first n tail rec n, why not see it as a partial application of function above? Oh, here. Okay. So in order to, yeah, it is, yeah, you can do it like this. Yeah. So this is also the same thing. Yeah, so you can sort of see it as partial application as well. So good question. So I think we explicitly have an n here, which I passed there, but you can instead just define this value, which is sum of tail rec n, which is a partial application of this function. Really good observation. I think both are valid. Actually, this is more preferable to the previous one because that's not idiomatic. This is much more idiomatic. But the types remain the same, right? So just good question. I think I really like that question. So what I would recommend you to do is try to trace this function, right? Just so that you um, understand the reasoning behind why this function works, because we will use this trick of this auxiliary accumulator all the time, right? So this is the standard trick that we will do, and we will write a natural recursive function and we'll say compute the sum of a list or something, right? And then you will have to use the accumulator. So just go through, just trace this function, right? Fire up this notebook and just write trace this function. It will tell you what's happening. And I think that's all I have for functions. There are a lot of concepts here, but you can sort of break down the concepts into simpler pieces, right? Actually, much of the concepts are not fundamental. They're just syntactic sugar over the core features. So it is important to understand which of these are core features. I think there is enough materials here. Go read the chapter 2 in CS3110 textbook. Right, this is linked off of the schedule in the course web page. You can click on it. It's an online book. It sort of covers the expressions and functions. And it's a really good read. It sort of gets to the point, and it doesn't digress, and it's very simple. So yeah, so the question, there are two questions. So how does this is all because we are just returning the value without modifying it. Correct. Yeah, that's correct. Because if you want to modify the value, right? Modification is some operation that you are doing after the return of the call, right? So if I do 1 plus here or something, then it's modifying the value. It's not modifying a value, it is returning a different value. And that computation is sort of left to do, right? So I think that's the reason why this actually works in practice. And the next question is, how does it recognize a function as a tail rec or just a rec? So this is compiler analysis, right? So compilation sort of so it's so there is a standard compiler pass, right, where you sort of see um, build an abstract syntax tree, right? So all of this you will study in the compiler's course, and then what you will see is that this recursive call is the leaf in that abstract syntax tree. So a leaf is what you do last, right? And if the thing that you do is at the leaf position, then it will it's a tail recursive call, and the compiler can automatically identify whether something is tail recursive or not. It's not complicated actually. It's very simple once you. But I suspect that if I start talking about it more, you won't yet have the vocabulary to understand what I'm saying, but you will get it in a few classes while you study tail recursive calls and compiler analysis and so on. Can we now call sum of first and tail rec 05? No, right? Because the second one shadows the first one. So if I say 0, this one, um, yeah, so here it complains, right? It sort of tells you what the type of the two functions are here, but the second function has the same name as the first one. So only the second one is left. So if you call that with two arguments, then OCaml complains saying, oh, this function has type int or int. It takes an integer, returns an integer. Why are you applying it to too many arguments? Right? That's the thing. But if you don't want to shadow it, you can do it as say _1, right? And then you can do _1, 0. So this will work. What happened? Oh, okay, not _1. Sorry. Yeah, this will work. It's just a matter of shadowing. Shadowing is what we've seen earlier, so that's why you can't call it. I think I'll stop here. I'm 3 minutes over. So there are more questions. I'll keep answering questions, but anyone who needs to leave can leave. How did the memory get reduced? We added one more argument to our function. It's not about memory, right? It's the stack memory that is we are reducing. So we are not. So the problem earlier was not that we were using too much memory. It is just the matter that we are building up stack frames, right? We were building up these stack frames earlier. So it is not this extra memory for one variable. And that doesn't actually cost much, right? We are no longer building stack. That's the key bit. So any other questions? No, okay. So I think you should probably stop here so that you can have a small break before we start the next class. Okay, thank you very much.